large bar at W, so probably W is the letter. Right, so you're with me, that's good. I actually ordered them down here so that you can rank them from the most frequent in the code to the least frequent, so in the ciphertext. And the second one is G, and then we have E, K, O, U. Well, I don't know all the letters rank in frequency off by heart, so what I do in that case is I get a little bit more data, so I'm going to look at a text from Moby Dick. And I didn't take the whole of Moby Dick, I just took about 1,600 characters, and I'm looking at their frequency. And so that gives me an idea of what the frequency in English looks like. And so here we have the letter E, in fact, is much more frequent than any of the others, and the second one's probably the letter T. And if I order them, you'll see how they order down. So you can see that by pairing, in some sense, the frequency in the code with the frequency in English, and here I've done it left and right, we could go down and we could help ourselves and actually break the substitution code. The advantage of doing that is that we have quite a lot of signal in the frequencies of the different letters, and so it's possible to do. And in fact, if you start replacing the letters, the E, the T, and so on, you come to a point where you can read the text. So it says, in a medium saucepan, bring the milk and cream to just below a boil over medium-high heat. Okay? Probably some of you who know me have some prior information on what the recipe is. And if I take the whole recipe, it's a recipe for creme caramel, and the medium saucepan, bring the milk and cream to just below a boil over medium-high heat. Meanwhile, mix together the egg yolks and so on. In code breaking, there's a big advantage over statistics. The proof of the pudding is in the eating. That is, you can see whether you succeeded in breaking the code practically immediately when you see the text. And here is the ciphering, what I call the permutation, the ciphering permutation. And this is what we call, and we will call, a monoalphabetic substitution code. There are lots of them. There are almost more than 10 to the 26 different codes that you could do in this way. And this was already used in the 9th and 10th century, and they were broken at that time already. So the diplomats later decided around 1550 already that this wasn't an acceptable code, and they needed a code in which you could change the substitutions. So they invented a method, this is a device actually with a ring, where as you go along the passage, you're going to take a different substitution code, and this is a device from De La Porta, and this code was called the Divisionnaire code because it was written up by Divisionnaire, and in French they called it the chiffre indéchiffrable because it wasn't broken for almost 3 centuries. So it's a very, very hard code to break. Let me tell you a little bit more about how you would encipher something. So if I take the text in English here, in a medium saucepan, and I write underneath a keyword, so here I've put ambidextrously, and the letter A won't have any effect. It adds 0 to I, so here I becomes I. But for instance, B will add 1, so A will become B. And all of these letters, as you look down, you see that they're being replaced. So N and B is the code here, and so it's replaced by O. So as we go along, we get here, this is our new cipher. And if I try to break it using my method, the frequency analysis, this is what happens. So here I have the frequency on the left, which is the frequency of English that I got from Moby Dick. And on the right, I have a very, very flattened frequency. And so it's obvious that it's going to be quite hard because the differences between the different letters is very, very small. And also, every part, every column has its own enciphering. So it's not even one-to-one along the text. So you'd have to know the keyword length and have a long enough text to be able to do frequency analysis on that text in order to break it. The first to break it actually was Kaczynski. And he had a method which I'm going to let you try and do by just hypnotizing yourself on the screen for a few minutes. So try to see, if you look at this whole mess of letters, if there's anything that jumps up to you. Well, this isn't on the handout, so you haven't been be able to prep on this. Is there anybody notice anything on the... Mum. Okay, so here we have, actually, it's more than mum. We have quite a long stretch of letters which are exactly the same. Now, in fact, if you consider the probability of having such a long stretch, that probability is very, very, very small. So it's not really, it's not by chance. It's actually the fact that the difference between the first letter here and the first letter there is a multiple of the keyword length. And so this can occur, and I'm going to show you why it can occur, but what happens is these, as they match, they've been a matching word in the original plain text, and then there was matching letters from the keyword. So they were enciphered in exactly the same word. So the same method of finding matches is at the basis of another very important index, which is called the coincidence index, which counts the number of matches in columns or between 2 random letters. So let's start with the columns, and if I organize my text, again, exactly with the number of columns, which is the length of the keyword, I know it to begin with because I just want to show this to you, and I put a star in every column where I have 2 letters who match in the column. So here M matches with M and M, they all have stars underneath them. Here I have T, and here I have an R and an R. So that's how the stars appear on the left. On the right, I have the original text, and I also have the matching letters, so R and O. These are the same letters because the first letter of the keyword was an A, so they're the same. But what you notice with the stars is they have exactly the same pattern as in the original text. So the stars in the ciphers occur in the same place. They're what we call invariant. And that's a very useful property. And it was discovered and used very carefully in cryptography from the beginning of the 20th century on. So in order to compute, in some sense, whether 2 messages or whether we have the columns here have the same alphabet, we need to compute a score. We have something called the coincidence index, and this is what it means. It's you take two letters at random, and you look and see what's the probability that they match. Well, if you have two, this is your number of letters, so I took my text from Moby Dick, and I have 1,500 letters. I have 122 A's, I have 18 B's, 31 C's, and so on, and I can look at the number of ways of having matching letters. So I can either have two A's or two B's, or here two Z's, and so on. And when I count the number here and divide by the number of ways of just picking any two letters out of 1538, this is that number, which is more than 1 million, I get a ratio of about 1 in 15. So I have about 1 chance in 15 of having a match if my language is in English. If you do this in the case of the uniform, you get something quite different. And let's do the flattened uniform distance first, and show you that if I had 100 of all of the different letters and I computed what's the probability of a match with those, I get 1 out of 26. So the coincidence index in a completely flat and divisionaire, if you had a very long keyword, for instance, would qualify, would be 1 in 26. So this idea of computing this index is actually due to a geneticist, William Friedman, who went on to be a very good cryptographer, and he wrote a whole book about the coincidence index, and he did developments and expansions, and he was the first person really to understand that cryptography benefited from using mathematics. Before that, most cryptographers were linguists, and people who knew a lot of languages. They came from the diplomatic corps, and William Friedman hired Saul Kullback. He hired many mathematicians in the service, actually, of the US in the 20s, and he's the man who wrote Purple during the Second World War. So he's a very clever cryptographer, and this index was very, very important in everything we're going to see. So, where are we? In 1930, we have the knowledge of cryptography. We know how to break divisionaire using the coincidence index. Oh, sorry. We know how to break the monoalphabetic substitutions, and in some sense people did understand that the most unbreakable code would be a divisionaire with a very, very long key, or a key that's as long as the message. But if you know how to transmit a key as long as the message in a secret way, you don't need divisionaire in some sense. So there's a difficulty in the transmission of the key. It was at that time that several companies, and in particular in Germany, there was a commercial company called Scherbus, which developed a machine which was trying to be a mechanical one-time pad. And that machine is called the Enigma machine. So this is the machine that the Nazis started to use to communicate. They'd been burnt by the fact that the British had broken their code during the First World War, broken the German code, and they'd actually been quite arrogant and publicized it, and had said, well, we broke the code, and So the Germans took it very seriously to have a good machine, and this is what the machine looked like. So here we have a plug board in the front, there's a keyboard, just like a typewriter, and we have lights here, and 3 wheels, which are scrambling wheels, and they have settings, they have little windows. And these are called the rotors, and this was all carried in the field, so it had a battery pack, and it was used to encrypt, and then the messages were transmitted through Morse code. So the basic component is a scrambler, and there are 3 of them side by side, these 3 wheels, and you can think about them as monoalphabetic substitution permutations. And so they're just wiring letters between each other. There are a couple of extra twists to it. As you see, they have little cranks all along, and in fact, the wheels on the right is like an old-fashioned odometer would go around, and there's a ring on it, and so there's a setting at which the rings could work. But that's the basic machine. And so just so that you can see what's happening, here, if I press on R on the keyboard, the electric impulse will go around this, and then it will go and light up the letter C. So that's the way that the machine worked. It was an electrical machine, and it went through the 1, 2, 3 scramblers in this direction. Here we have a reflector, and then 1, 2, 3 in the other direction. And here I have the little wheels, which are the settings of the machine. So that's what the machine looked like. And if you like, I can be brave and get out of this and show you a nice little simulation, just for the purpose of, I have several simulators up, and there are several of them that you could actually do this on the web. And so that's my little simulation of how it goes along. And this is a better simulation because it shows you what happens. So as I type a letter, you see what's happening? Different letters are coming out. And if you pay a lot of attention to the letters that are coming out here, what you'll see is the letter A never occurs. So I type A all along here, and I'm getting a lot of different letters. And mostly I don't get the same letter twice in a row, but I won't get the letter A. So it never encodes for itself. So let's go back. That's easier said than done. There we are.
Why does it give you when you press it the second time, I see something different?
Yes, the second time it will give me something different.
Why?
Why it gives me something different is because the wheel on the right is like an odometer. And so as I go, I type once, it goes around once. So I have a different scrambling. So it's going in a different place. So every time it's a different, and so it's like a divisionaire. That is, it's changing, it's a polyalphabetic cipher at every time I type. So every time I type, I get something different.
Why can't you do the letter?
Sorry?
Why can't it repeat A?
Oh, that I'm going to tell you. Sorry. I'm going to tell you why it can't encrypt A as itself. And it was hardwired to do that, and that was a specific constraint that the Germans wanted, and it's one of the mistakes that they made. And it made it much easier for the Allies to break the Enigma because of that. So now we're in 1931 in Poland, and the Poles are very, very worried about what's going on. And the Nazis, they know, are gearing up in a very aggressive way, and they've decided to work very hard on the cryptography and try and break the Enigma. And what they did was they hired 3 young math students, Henryk Zygalski, Jerzy Brzezinski, and Marian Radusky. And here you see the 3 of them actually in Uzès in the south of France in 1940. But they got to know each other, they worked together. Radusky had not only done math, he also did some statistics in Göttingen. They had the challenge of trying to break the Enigma. And what did they have? In summary, they had this machine where they knew about the reciprocity condition. So at the same wheel position, if you type C, you get R, and if you type R, you get C. Now, if I type R and then type C, I wouldn't get R back because it would have changed position. I have to put the wheel back once so that I get exactly in the same position. But then it's also non-crashing, so as I said, A cannot encipher A, and they knew about the turnover notches on the different wheels. There's different notches like an odometer that would make it go around, and there's also a plug board. So the plug board increased the number of possible settings in some sense, so the period of the machine a lot, and it just inverted 2 letters, so it was transpositions here. And in 1931 they were using just 6 wires. Now they had the commercial machine, but what they didn't know actually was what the wiring in the real wheels, the one that was being used by the army, was. So they have an imperfect model, commercial machine. They have the constraint that the same machine are used to encrypt and decrypt, so that's the property CRRC, and they have the data. Now the data they have is the data you have on the handout. You had a look at it, some of you who arrived early, and I'm going to show you how we can use pattern searching and data mining and look at some of the mathematical properties of this data to find how the machine was wired. So here's the daily traffic. So when I say it's the traffic, it's actually the first 6 letters of all the messages that were sent that day. And here they had between 60 and 100 messages every day that they intercepted, and they collected all these first letters. And so for those of you who've been sitting looking at it, does anybody notice anything remarkable about this data? Do you think that those were just 6 random letters, that they was generated uniformly randomly as 6 random letters? No, right. And so what's wrong? Why doesn't it seem random? There we are. There's a lot of repetition. So here I have 4 times the same. Here I have 3 times the same. Here I almost have 5 times the same. Why do I say almost? Here we have what we call in statistics an outlier. This is all humanly recorded by people who are listening into the Morse code, so it's quite often there could be mistakes, but it's definitely, there are many too many repetitions to say that these were random. And so the repeats tell us that in some sense these were very systematic. And more than the repeats, you can also look at something else about. Did anybody notice anything else about the data? So if I, instead of looking at the repeats, suppose I look at, here I have, the first letter is S. Here the 4th letter is S. Here I have, the first letter is R, and the 4th letter is W. And here I have T and E. So it seems as if the letters 1 and 4 are tied. And that gave an extra clue. And then what the Poles did, which was really clever, was they took the messages that, for instance, these messages that had SYX and SCW, they took the 2 messages and they computed the coincidence index on those messages. And they saw that they matched. They have a coincidence index much closer to 1 out of 15 than 1 out of 26. And so they were able to see that these were what we call in-depth. They were aligned, they had the same. So this told them that these 6 letters actually made the setting of the machine for the messages. And this was then confirmed actually by information from spies that were given to the French and communicated to the Poles. This fact about the 1st and the 4th letter is actually also true if you look at other letters. So here the 2nd letter is X and the 2nd letter is T. And here we have the 2nd letter X and the 2nd letter T. And here D, BV and BV. And here we have JP and JP. So all the letters 1 and 4, 2 and 5, and 3 and 6 are tied. And that's what inspired them to say that can be explained by having the same indicator, say ABC, repeated, ABC. And so if the same letter is at the 1st and the 4th position, then the output, the machine is deterministic, it'll give you the same thing. So in order to understand this a little bit more, let's come back to what we started with when we started talking about permutations. So we said we had a reordering of the letters, and that's a permutation. Here I'm doing a little example with just 5 letters, and here I have a transposition CD, and here a permutation ABE. And we write it down ABE, CD. And we can write down the inverse just by changing the direction of the arrows. So here AEB and CD, it just gives the same thing. So these are all permutations which are very small, 5 things, but it's the same idea on the 26. Mathematically, permutation is special. So when you take the inverse of a permutation, you get another permutation. When you multiply permutations, you get another permutation. So the mathematicians call it a group. So what happens in the group stays in the group. So the Enigma permutations are what we're going to work with, and we're going to write out a small equation of what the Enigma permutation is. So if I follow my wiring, and so I typed R, I go through N, I go through M, I go through L, I go through R, and then I go L in the other direction, so I call that L minus 1, it's the inverse, M minus 1 and N minus 1. So that's what I just did, and that pi is what I call an enigma permutation. I've left out the checkerboard, and I've left out some of the details, but I think that's a useful model, and this is the setting of the wheels at that time, and then when I'm going to go around the next time, the setting will be slightly different, and the E will become an F, and I'll get a slightly different setting, but I'll be able to write it actually as a function of this. So in the first setting, I'll call it pi 1, the second letter, I'll call it pi 2, and so on. Here, I've coded up a little bit, part of it, I didn't have room for all of it, but this is the reflector, and what you see is A is wired up to R, and B is wired up to I. So I write this down, that A and R are switched, B and I are switched, C and T are switched, and so on. So R is a very special permutation. It's a product of what we call transpositions. It just transposes the letters. It's very much like what the plugboard did as well. And it turns out that this R here is the only one, it's just in the middle of the forward product and the backward product. And here there's a little theorem which says that if you have a permutation and it's written as the forward, there's a product of permutations and its inverse, then these two, pi and R, will have the same cycle structure. They'll have the same bracket forming. And sometimes these are called boxes. And so these has 13 boxes, each with 2 in it. And here I also have 13 boxes, each with 2 in it. It's because of that actually the enigma just, when you typed in a letter, it gives you, say I type in R, I get C. So I would have R and then C here. And if I typed in C, I get R. So the reciprocity condition is guaranteed by this. And it also guarantees that there are no fixed points. So there's no point which is mapped to itself. So that's the working structure. And in fact, it decreases enormously the number of possible permutations. These are special permutations. How can I use that knowledge to find the wiring? Well, I just take one of them. I'm going to work on just one of my indicators. There was this SYXSCW, which was quite frequent. Let's work with that one. And suppose that my indicator is ABC, ABC. Well, in fact, if you look carefully, that will enable you to conclude that S multiplied by pi 1, pi 4 has to become S. And here the Y, if I multiply it by pi 2, pi 5, I have to get C. And so this piece of information, just this hexagram, already gives me 3 conditions on these products. And if I go through all the daily traffic, this traffic data, I can actually write down lots of things about those products. I can go all the way down to that. Now I won't explain to you all the equations that they solved and how they solved them. Just to tell you that, in fact, the only way of getting 2 fixed points for pi 1, pi 4 is to have AS in pi 1 and AS in pi 4. So we already know that from very, just one of the hexagrams. And you can go through and you can find that these fulfill the equations. And from that, the Poles were able to find what the wiring was for their wheels. And this was an enormous progress because that made that they could make machines. They could make their own Enigma replicas and they could use them to do what we call forward analysis. So they took a lot of cribs like weather and things like that. And they typed those words in many, many different settings. And they could do analysis of the block structure of the boxes. One of the things which is curious, they went back to look at what were those ABC indicators that were being used. And it turns out that the way the operators were typing the indicators were actually a lot of letters which were repeated, so F, 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 or S, 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 A, A, A is the one that we were studying, Q, 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 and then all the others are contiguous letters on the keyboard. And so the Nazi operators are no different from you when you're typing in your passwords. None of your passwords are secure. It's for sure that we do a very bad job of choosing our passwords. So that if you have to choose them, these are certainly not randomly chosen. And there's actually only one here, ABC is the only one where the letters aren't next to each other on the keyboard or repeats. So it really was, so this comes from a very nice book. If you're interested in this, I put some of the references at the end, but Friedrich Bauer has a very good book about what happened and how these were broken. So I'm not going to go into all the details of all the things that the Poles did because they had a first machine that they called the Bomba machine, which was what we could call a contradiction machine, in which they could find some of the settings. They used a lot of guesses, they used mathematics, but they did a lot of data dredging on patterns, and they did a forward analysis with cyclometers where they made the cycle structure for different settings so that they could go back and find out what the settings were from cycle structure which were invariant. Came 1939, and the Germans were just about to go into Poland, and the Poles left with all the cryptographers left with their material, and they went to Paris, and they met Dilly Knox, who couldn't believe it because the British had been trying for 8 years to break into the Enigma and been completely unsuccessful because they hadn't thought of how to wire from the keyboard to the first wheel. It was very different in the commercial machine, and Marian Rejewski just had the idea to try A, B, C, D, E, F, G instead of the keyboard order, and that worked. It was a very orderly wiring. And all the material went to Bletchley Park. So Bletchley Park was chosen, here it is here. It's on the train between Oxford and Cambridge. And so they were mathematicians, linguists, chess players, crossword puzzle. They were all together at this mansion. And they were working on breaking codes, and they broke many of the German codes through the war. The work I'm going to talk to you most about was led by Alan Turing. So Alan Turing had many sides to him. He did a lot about computability of numbers, but as his junior thesis, he wrote a paper on the central limit theorem for non-identically distributed random variables. He didn't know at the time that it had already been done by Lindbergh, but he certainly had a very good feeling for probability and statistics. And here I'm just showing you, this is typed up by Turing, and this is his own words. He wrote a long document called The Application of Probability to Cryptography. And the only thing there are several things which are really sad. This was only released 2 years ago by the British government, or 3 years ago. And it's a real shame, and it's a wonderful text about how do you use probability to combine evidence. We know a little bit about what happened because he worked with other people who published, but this was kept completely secret. So I'm not going to read you the whole text. I will read you just a sentence which explains very well his understanding for what probability is. And so, for instance, if it is known that 20% of men live to the age of 70, then knowing of Hitler as a man, we can say that the probability of Hitler living to the age of 70 is 0.2. Suppose, however, that we know that Hitler is now of age 52, so we have more evidence, we have more information, the probability will be quite different, say a half, because 50% of men who have achieved the age of 52 live to 70. And the odds of an event happening is the ratio p over 1 minus p, where p is the probability of it happening. So I'm not going to go through the whole text, but this was a very insightful definition, and it led him to be able to score evidence, and I'll just show you on this example how he did it. So if you want to know how much evidence, how much is it worth to know that Hitler is 52, you can compute, the probability that Hitler lives to 70, given that he's 52, is a half, and so it's 1-on-1 odds. And the probability that Hitler lives to 70 is 1 out of 5. So we can write, and he writes, the posterior odds is equal to the prior odds times the factor. And he calls it the factor principle. Today we call that the Bayes factor. And you write the odds 1-to-1 equals 2 over 8 times the factor. That gives you a factor of 4. And then he measured it in log base 10, actually 10 times log base 10, and he called that a deciband. And later on they used half decibands as their as a unit, and the idea there was the parallel with the decibel, that is, how much evidence can you hear? And the idea is they're listening to their data, and they use this measure to listen to the data. So this is the text where he explains quite an interesting problem of looking at the statistics of people who die in their beds and people who die of heart failure, and he uses that to ask, can I compute what are the odds of this person I find dead in their bed having died of heart failure? And it's very touching that he